realized it was huge scope, and we have effected a quite considerable scope retreat. And the proposal now is simply to introduce a matrix class into the standard library. Just wanted to make that clear. But I'd like to take a moment to talk about this first. The biggest problem that we have in the C++ community is that there are more problems to solve than engineers to solve them. And especially at this time, we need problem solvers to solve the hard problems. Historically, software engineering has been a very inclusive environment. I usually give the example of Margaret Hamilton. She was the director of the software engineering division of the Massachusetts Institute of Technology Instrumentation Laboratory. They developed the onboard flight software for NASA's Apollo program, and she is one of the people credited with coining the term software engineering. But now, however, we appear to be heavily biased towards white men. We all know this. And we have very low gender and ethnicity diversity, and we as a species need to fix this. We need to recruit more people. So if you're interested in helping, please visit the website. We have a Discord server as well. Please join that. It would be great to see you. Thank you. So here's what to expect. We'll start with a speedy refresher on what linear algebra actually is, and then talk about the nature of a linear algebra library. And then we'll look at the library being proposed and how to customize it for your own use. Now, if we have time, we'll look at applications to color space management. And if we have lots of time, we have a simple application for geometry. I've run through this talk several times, and each time it takes a wildly different amount of time. So you can talk to me about those last two topics if we don't reach them afterwards. What is linear algebra? It's the branch of mathematics concerning linear equations and linear functions and their representation through matrices and vector spaces. So a linear equation looks like this. It's the sum of some products of coefficients and unknowns, and it has application to geometry for modeling the Cartesian representation of space. Color is typically represented as a triple of values. You're probably all aware of RGB. Some of you might be aware of HLS. And there are useful things you can do when manipulating color spaces. An awful lot of errors are made here. Solving simultaneous equations is probably the first piece of linear algebra that any of you did via row reduction. In fact, linear algebra underpins most of modern mathematics. It has applications in machine learning. Machine learning is just number crunching, really. And linear algebra features heavily in it. Most textbooks will start with the vector, or even the scalar, but we're going to start with the matrix and work backwards for reasons which will become apparent. So a matrix is an m by n rectangular array of scalar elements. And that word array is troublesome, obviously, and it's not the last time that we'll have issues with glossary and repetition of words with slightly different definitions. And just as with the real number field, there are operations that you can carry out on matrices that match the scalar operations. So you can perform matrix scalar multiplication. This involves multiplying each element by the same scalar value, like that. You can perform matrix addition. This is somewhat constrained because you can only add matrices which have the same size. And that use of the word, well, in fact, the same dimension, and that use of the word dimension is also problematic because the dimension of a matrix is the number of rows and columns that it contains. It's nothing to do with geometry. A 3 by 3 matrix is not necessarily representative of three-dimensional space. There's no such thing as a three-dimensional matrix. All matrices have 2 dimensions, m by n. This continues to confuse people, no matter how many times I give this talk. Addition takes place member-wise, which is why the operation is so constrained. The matrices have to have the same dimension. As well as scalar multiplication, there's the big one, matrix multiplication. And this is constrained by requiring that the number of columns in the left operand match the number of rows in the right operand. I'm hoping none of this is unusual or peculiar to you. I just want to make sure we're all on the same page. Now, this constraint is due to the mechanism of multiplication. It's performed by calculating the dot product of every row and column combination, then retrieving the row from the left-hand operand and the column from the right-hand operand. And the dot product is itself a sort of linear equation. It's the sum of the member-wise products of the elements. And you can see in the example that the top left element in the result matrix is formed from the dot product of the first row and column. No one is looking blank. This is a good sign. And since we're taking rows from one operand and columns from the other, matrix multiplication is not commutative, or not necessarily commutative. There's a special kind of matrix called a square matrix. This has the same number of rows and columns. There's a special kind of square matrix called the identity matrix. So the leading diagonal, that is all the elements whose row and column index are the same, is populated with 1, and all other elements are 0. And multiplying any matrix by the identity matrix, or vice versa, leaves the matrix unchanged. So there we have an example of commutativity. Now there's an interesting property of a square matrix called the determinant, which is a single value. It's like a modulus, I suppose. It captures information about the matrix, like a median or a mode or a mean captures information about a set of numbers. Its calculation is the subject of considerable research effort, since it's used in several ways. A matrix can also have an inverse, and the product of a matrix and its inverse is the identity matrix. So we see that there are some analogues to the built-in types. There are well-defined meanings to the arithmetic operators, although post-increment and ordering don't really have any kind of meaning. One might choose to order by determinant, but that's an unusual activity. I've yet to find a use for that. Now, a vector is a special kind of matrix. Bear with me. It has only one row or only one column. A single row matrix may be called a row vector, and a single column matrix may be called a column vector. And the multiplication has two different forms, each with their own name. So the inner product is the name that's given to the multiplication of a matrix with a single row by a matrix with a single column. And this is achieved by performing a simple dot product, like that, and that will yield a scalar value. The outer product is the name given to the multiplication of a matrix with a single column by a matrix with a single row. And this will, of course, yield a matrix. Inner and outer product. So we have something of an abstraction problem here in that matrix products take several forms. And we also have a naming problem. Vector. Vector is already in use, being the name of the most commonly used container in C++. Now you could implement a linear algebra vector in terms of a stud vector and a matrix in terms of a stud vector of stud vectors. But that would be at the very least suboptimal for all uses. It would not even pass code review if you were to show it to me. Right, what's a linear algebra library? Now, I've written quite a lot of linear algebra libraries. In earlier talks, I said I've written 4, but I found a 5th. So I wrote a library during my linear algebra course at university. I studied a mathematics degree. I had an Atari ST. Anybody else remember Atari STs? 1, 2, 3. Oh, hello. Do come in. Yeah, the Atari ST, great piece of kit. Now, before this point, I was just doing geometry. I was using fixed point arithmetic. And I probably did write a linear algebra library without really knowing it. It was before I went to university, and I was just doing stuff to transform pixels on screens. It supported geometry and translation by addition, scaling by scalar multiplication, transformation by matrix multiplication, angle computation by dot product, and normal computation, computation of the normals to planes by cross product. That's not actually linear algebra. That's completely separate. That just happens to use matrices and a particular product. And this hints at a problem that we'll come up against time and again. So when I got my first PC, I I had an 80286, and I built a linear algebra library with fixed point mathematics. And I was using C and a bit of C++. I was using Visual C++ with Microsoft Foundation classes. But it was the same set of operations and the same set of problems to solve. My next machine came with a floating point coprocessor. I was delighted. Suddenly, it was a fantastic thing to discover. And people take for granted floating point calculations on contemporary CPUs, but there was a time when it was a very expensive piece of extra silicon. Now, I moved away from relying on C entirely and embraced C++ fully. And then I joined the games industry. That was great. And when the MMX instruction set came along, I didn't like having to share floating point with vector instructions. So the MMX registers were shared between the floating point operations, which meant if I wanted a matrix of floating point values, I couldn't use MMX instruction sets to do my operations. And I had a hideous time mucking about with all of this. But I got another machine and another processor, and I got SIMD by SSE2. It was the Pentium 4. And this was lovely, big jump in performance. Still the same set of operations, still a linear algebra library doing the same sorts of things. Then I got an AVX processor, registers got wider. Other parts of the team are buffing the linear algebra now at work. At my studio at Creative Assembly, there are people working on the linear algebra, keeping it optimal. Now I said 5, there is of course a 6th linear algebra library out there, which is mine and Bob Stiegel's. This is P1385. It's a proposal to add linear algebra support to the C++ standard library. At least that was its original name. It's now a matrix class for the standard library. Now the lion's share of this work is actually by my co-author Bob Stiegel. We agreed on the superiority of his approach. We both looked at our respective linear algebra libraries. His was better, so that's the one that we're implementing. Now I have several optimizations available to me. First of all, I know how big all my matrices are going to be. I'm just doing geometry. So I'm not going to be with 10 by 10 matrices. The largest matrix I have is 4 by 4. I also know that the scalar type is always going to be a 32-bit floating point type. And I know about my target processor, so I can use intrinsics and SIMD instructions. And I can make use of cache behavior. And I also know that everything's going to be dense. There are going to be no empty elements. This is a densely packed matrix. My library is optimized for this particular usage of fixed size, dense matrices. And there are many ways to optimize for other situations, such as sparse matrices of variable sizes. It's like string classes. Right, who here has written a string class? Come on, be honest. You've all written a string class. It's what you do. You write a string class because you don't like std string. It's the same with linear algebra. Everyone writes their own linear algebra library. It's perfect in every way. It's your special little snowflake. Nothing will touch it. But fundamentally, though, a linear algebra library consists of a matrix class. It probably consists of a vector class, and even that is questionable if you treat a vector as a special kind of matrix. And of course, infix operator overloads to operate between them. There are other libraries which don't use infix operators, which offer a simple function API, something like mul, vector 1, vector 2, or mul, matrix 1, matrix 2. There are uncontroversial operators like addition, subtraction, and scalar multiplication, but in the course of the development of this library, the asterisk operator has proven controversial. I say asterisk because that's what it is. It's an asterisk. You know, the array operator is actually the square bracket operator, or more precisely, the bracket operator. The round ones are called parentheses, and that's the parenthesis operator. I'm really quite particular about naming, which is what has caused so many of the problems that have beset this proposal. So, what do you call this operator, for example? Is it the bit shift operator? Is it the streaming operator? Is it the chevron operator? It's called a chevron. And I think it's better to name the operators after the character rather than the most common usage. Operators are meant to be overloaded and given different uses according to the context. So this is the square operator, the square bracket operator. And in this font, it looks rather unusual, but that is actually the open and closed square brackets. At the moment, I have to deploy this syntax in parentheses using to access elements of a matrix. But what I'm used to seeing in textbooks is this particular spelling. We have brackets and a comma. And this is complicated by the comma operator in this context. Now, there was a proposal which was passed for C++ 20, P1161, which deprecates uses of the comma operator in subscripting expressions. It's in Annex D of the standard, if you really want to find it, but believe me, it's there, it's lovely. And building on this is P2128, which seeks to enable multi-dimensional subscripting, and that was passed last Tuesday at the last plenary of the WG21 C++ Standards Committee. I know, I am delighted, I really am. So we're freed from syntaxes like this, with pairs of square brackets to access arrays of arrays. Anyway, operator asterisk. This isn't what you see in textbooks. What you see is this. It's an X, or multiply sign. It probably does have a proper name, but I haven't been able to find a good one, not one that everyone agrees in. It's not described in the Unicode descriptors. We can't have an operator X. That would be silly. It's the most commonly used variable name, for one thing. So we can't just have it as a special operator. What will become of us all if suddenly we decided, right, operator X means this? All our 50 years of code has to be swept aside now because X means something different. If we were allowed Unicode, we could have operator, and this is called modifier letter small x, which it does actually sit in the basic multilingual plane, so it's quite accessible. But I suspect that's an abuse of a modifying character. But we've been using the asterisk operator for so long, it would be unusual to revert to something more correct. So what does it mean to multiply two vectors to form a product? So while taking this proposal around the committee, I found out that there is a field of pursuit which makes use of something called the Hadamard product. Anybody here use the Hadamard product? No, that doesn't remotely surprise me, and I am delighted to see that. Oh, you do. Okay, great, thank you. I'm sorry you're in a minority. It helps my case that you are in a minority. That's good. The Hadamard product is simply a member-wise multiplication, and if you know anything about linear algebra, that destroys all the transforms embedded within your matrix. And it can be applied to matrices as well as vectors. And it makes me slightly queasy, because the main application of this has nothing to do with linear algebra. Is that correct?
Yeah, I don't even remember when I used it, but I think at some point.
Good, excellent. You make my case stronger with every statement that you make. Thank you. It's simply multiplying an array of numbers by another array of numbers in situ. And this array of numbers is called a vector or a matrix because it looks like a vector or a matrix and is accessed with multi-dimensional subscripting. And it's not quite right, it's wrong. It's so disappointing, it really is. There are quite a few libraries out there already. You know, this isn't the first one. Just a simple Wikipedia query yielded plenty more than I knew about, so let's take a look at some of them. The first of which is BLAS. Who's heard of BLAS? Yes, good, yes, this is the granddaddy of them all. It was first released in 1979 as a Fortran library. And it prescribes a set of low-level routines for common linear algebra operations. There are C bindings, that's helpful for us. And there are many implementations optimized for speed on a particular machine. You can buy the BLAS for your processor. Buy, download, I think it's downloadable. Do you buy BLAS or is it just free for anyone? Special. Anyway, I'll come back to that when I've found out. Right, there is a C++ API for BLAS, of course, called BLAS++, which implements much of the functionality for all your linear algebra needs. There's your interface. BLAS supports single and double float precision and single and double precision complex numbers. There's also, of course, boost.ublas. But the last significant change to that, as far as I can see, was in 2009, which predates C++11 by the application of simple arithmetic. So there's no const expra, there's no except, there's no concepts, there's nothing like that. There are 3 levels to the BLAS API. Level 1 consists of all the vector operations. These names are very short. It dates back to a time when only 6 characters were significant. It makes it very hard to provide meaningful names when you're only allowed 6 characters. Generate modified Givens plane rotation, ROTMG. Level 2 contains the matrix vector operations, and level 3 contains the matrix operations. And this gives us a good starting point for the kind of API we might want for a matrix class. You can see a fair amount of repetition varying on matrix types. We've got Hermitian, symmetric, and triangular matrices. And for various operands, matrix vector, matrix matrix. And we have a set of operations that's different for vectors from matrices. It was standardized by the BLAS Technical Forum, known as BLAST, because why not? If you're going to call the BLAST Technical Forum, of course you're going to call it BLAST. It's fun, it's a good word. And there's a companion paper to mine which seeks to introduce a BLAS interface to the standard library. So you simply have BLAS in the C++ standard. I welcome this paper, and it would provide a good default implementation for this syntax proposal. These 2 proposals, the BLAS implementation and mine, are complementary, and they actually get known as the syntax proposal. This is the syntax proposal, and the BLAS proposal. Next we have Eigen. So this is a C++ library with matrix and vector templates. Dimensions can be declared statically or calculated at runtime. There's a span object for viewing unowned data. And the API consists of member functions. And this is another thing that makes me a bit queasy. I don't like member functions very much. I've used stdstring. There are a lot of member functions in stdstring. It's the poster child for this. I think there's over 50 member functions. It's a huge, huge number. I should remark that although I've mentioned inverses and determinants, these won't feature in the proposal. We're purely defining the matrix type and the infix operators. People can layer additional proposals on top of this. The scope for linear algebra, as I said at the outset, is huge, and we had to effect a great scope retreat. So it's just the matrix class and the infix operators. Here's some sample code. This is Eigen sample code. I particularly like the initialization of vector at the bottom, using the chevron operator and commas. Right, dlib. Anyone use dlib? It's a good library. It's a vast, vast library of useful things. The matrix classes use expression templates for optimizations like loop fusion. Anyone written expression templates before? Cool. Do you find that they're completely illegible? No? I need to talk to you about expression templates then. I've never come up with legible expression templates, particularly in the debugger. I'll talk to you later, thank you. I've described expression templates in other talks. If you want to take a good look, Wikipedia actually has an entire page on expression templates, which makes illuminating reading. Is Klaus here? Or did he leave? Klaus Eagleberger wrote this library, Blaze. And he's a strong supporter of the linear algebra proposal. It's a modern library. Well, his is a modern library which is tuned and customized for many different hardware environments, rather like BLAS. It's got static and dynamic sized vectors. And our proposal lives at this address, g21.link/p1385. Do note that down or take a photograph. As I said, it's known as the syntax proposal to separate it from the BLAS proposal. And the purpose of the proposal is actually just to reserve the identifiers. Because one of the problems that we have with Eigen and Blaze and all of the others is they have different names for what's essentially the same thing. And this makes interoperation very difficult. It's very difficult to write higher level stuff that will work for everyone. If you want to write a high level linear algebra set of linear algebra functions, You have to decide, am I going to support Eigen or Blaze or BLAS or all of them because I want to write 3 versions of the same thing. It's rather like developing a library for the standard at the moment. I have 3 compilers to support. Actually, I have lots, but I'm just going to support Clang, GCC, and MSVC at the start. There is another library in Boost called QVM, which is short for quaternions, vectors, and matrices. I don't like quaternions. Everyone should look up rotors and stop using quaternions. Rotors, R-O-T-O-R-S, much clearer than quaternions. If you're involved in any kind of 3-dimensional physics or space or anything like that, look up rotors. You will thank me personally. You will come and find me. You will bring me cake, I can assure you. But anyway, the QVM defines adapter traits for converting between different libraries. And this is something that could be added to the standard library afterwards so that you could interop more easily and effectively between standard linear algebra and Blaze, or Eigen if you're stuck in one of those libraries and you can't move without great expense or great modification of your code base. This proposal is very small in scope. I'm going to keep saying that. It's a small proposal. It's as small as we could feasibly manage, and we expect others to build on top of this. Right, any questions so far? Great, nothing controversial, that's good, thank you. Right, so let's look at the proposed library and consider what customizations we will need. When we declare a matrix, the obvious thing we want to be able to do is specify the type and also the arrangement of the elements. So here's an example of a trivial matrix. Stud math matrix float 3, 3. So looking at that, you may be able to guess that it's a matrix of floats, arranged in 3 rows of 3 columns. Unfortunately, we need to accommodate matrices whose size is not known at compile time. Stud math matrix float. And this represents 2 different storage strategies. So in the paper, we call these storage engines. If you know the size of something at compile time, you can probably store it statically. If you don't, you're going to have to store it dynamically. So let's talk about designing the storage engines, because with compile time storage, we're very fortunate. We know how many objects we want to store, and we know how big they are. And this gives us an object that looks like this. So it's TRC, elements, rows, columns. With runtime storage, we need to know about the type and how we're going to allocate. We can't parameterize the row and column count because we don't know what they are. So we need an object that looks like this. Type A for allocation, which leads to a typical usage that looks like this. It's starting to get a bit large, this syntax, as you can see. It's a bit of a mouthful. We could use aliases to help, but we still have something of an additional teaching burden. We have 2 types of storage engine to talk about. There are some aliases. So we could say geometry uses automatic storage of floats 3 by 3, which would give us stud math matrix geometry M1. But this problem has already been solved, as it turns out. A rather elderly proposal, P00009, that's old. It's from September 2015, when we started using P papers in the committee. It encountered just this problem. In fact, it's older than this. It started life as paper N4355, back in about 2013. I'm going to do what you should never do, and read the slide and the next 2. Bear with me, it's important. So from the first revision, multi-dimensional arrays are a foundational data structure for science and engineering codes, as demonstrated by their extensive use in Fortran for 5 decades. A multi-dimensional array is a view to a memory extent through a layout mapping from a multi-index space, domain, to that extent, range. Traditional layout mappings have been specified as part of the language. For example, Fortran specifies column major layout, and C specifies row major layout. Such a language-imposed specification require significant code refactoring to change an array's layout, and require significant code complexity to implement non-traditional layouts, such as tiling in modern linear algebra or structured grid application domains. Last one, a multi-dimensional array view abstraction with polymorphic layout is required to enable changing array layout without extensive code refactoring and maintenance of functionally redundant code. Layout polymorphism is a critical capability. However, it is not the only beneficial form of polymorphism. So the proposal, the MD-span proposal, specifies a new class called extents, which is an n-dimensional descriptor for describing the size of an array. It also defines a constant called dynamic extents to represent extents not known at compile time. In fact, during the development of the proposal, we were encouraged to take a lead from MD-span in interface design. And we're now in the position where MD-span can be used to implement part of our matrix class. But back to matrix storage engines, our class is starting to firm up. We can now specify a static or dynamic storage engine with this prototype. Like this. And this is preferable since we've isolated the dynamic versus static choice to a single parameter within the template. And we have one more thing to pay attention to, and that is the layout, row major versus column major. Now, you will recall the discussion in the original abstract P009 about array of structs versus structs of arrays, if you've read the paper. Everyone should read the paper, it's a great paper. Beside the issue of C versus Fortran, specifying different layouts, some hardware benefits from particular orientations. Some hardware will prefer you to go breadth first, some will prefer you to go column first. P0009 comes to the rescue again with the matrix layouts type, row major and column major. So it's getting bigger. On to the next problem. Right, customizing the library. This is a simple enough piece of code. What would you expect to see on the standard output? Oh, you've all been burnt by the quiz, haven't you? All right. Who guessed 3.5? Did anybody guess 3.5? Yay! You're all professionals, brilliant. There's a very convenient aspect of C++, which is implicit conversion. Okay, the left-hand operand is of type int, the right-hand operand is of type double. There is no operator plus int double. Mixed type arithmetic is not directly supported, but the compiler is allowed to perform an implicit conversion on the operands to find a suitable overload. And there are precedence rules you can find on cppreference.com when it comes to overloading. They are surprisingly detailed. I alluded to them yesterday. Has anybody gone and read them in their spare time? Oh, excellent. Did you find them detailed? Yes. Yes, you did. The preferred conversion is from int to double. And this may be troublesome if the int cannot be represented as a double, because many ints can't be represented as doubles. People do forget this, a lot of them. But that's what we have. Let's look at another example. Right, we're putting a complex number to standard output. Anyone know what this will print? Does anyone here use std complex? Yeah, 1, 2, 3, 4, yeah, okay, 5, excellent. Anyone know what it'll print? It wouldn't surprise me if none of you know, because it's remarkably, it prints in parentheses 3,3. Now I haven't specified any formatting to include decimal places or leading or trailing zeros. What about this? So this is std complex int 3 dot, 3 dot. It still prints 3,3 because the complex number is templated over int. So the constructor is looking for a pair of ints. And the compiler converts the doubles to ints, like that. So what about this? (3.7), 3.2. This is going to be a joke about rounding, isn't it? You can feel it coming, I can tell. It still prints 3.3. The compiler converts the doubles to ints only by truncation. So 2.9999 will be 2, which is most probably not what you want. What about this? Adding two complex numbers. Well, now it prints 7,7. This surprises some people. Why hasn't it converted to stud complex float? Stud complex double, and printed 7.7, 7.2. And what about this? Well, now it prints 7.7, 7.2. I initialized a complex of float with a pair of doubles. The conversion takes place at construction time, and then the addition takes place. What about this? It still prints 7.7, 7.2. The compiler converts the doubles to floats by narrowing rather than truncating, and the int to convert to floats. Again, the conversion will happen at compile time here since these are literals. What about this one? You're being so reticent, and wisely so, because it doesn't compile. That will not compile. What's going on? Well, simply put, the operators aren't defined. There's no operator defined for adding two complex numbers templated over different types. How could you? How could you do that? There's so many types that you might possibly want to instantiate complex over. The only ones that are defined are int, float, double, and long double. The rest is kind of, it's UB. But even then, we still don't have them. The built-in types that are part of the language are fully defined, as are their operations and their conversions. But stud complex is not a part of the language, it's part of the library. Now, defining operators for a few possible specializations of stud complex might seem wrong, but my co-author and I disagree. And we think this is an oversight. And there's an even more fundamental problem to solve in our case, because here are two storage engines with different element types. And here are two matrices with different storage engines. So what should the type of M3 be? You're adding two 3x3 matrices. Should work. We think that it should be legal. If you can add two different arithmetic types together, then you can add an array of them together. That's what we think. And if you can add an array of them together, then you can add a matrix of them together. And if you can add them, you can multiply them. The matrix should behave like the built-in types. And to achieve this, we need to work out a way of managing the promotion. To do this, we must at compile time examine the template parameters, and for each difference, work out a common type. So for example, if we have an operand storage engine with a double element type, and the other operand storage engine has a float element type, and the result of any arithmetic operation is going to be a storage engine with an element parameter of type double. I appreciate this is a wall of code. It calms down a little while. And this is an exercise in template metaprogramming, which I hate. And there's a whole talk possible on how we achieve this. But there is a slight problem, because when it comes to allocation, if either operand storage engine has an exotic user-defined allocator, then there's no way for the compiler to infer a common type. So we therefore have to expose another parameter to the matrix definition, which is the matrix operation traits. So for each of the four operations, we have three traits: element promotion, engine promotion, and an arithmetic trait, which I'll come on to in a moment. So during compilation, the traits class is used to form the resulting type of the operations. In the usual case, it's to be hoped that classes T1 and T2 would be the same, making the entire process quite trivial. But where they are not, the appropriate trait is selected to infer the correct promotion. So we update our basic matrix class to accommodate the operation traits parameter. It's getting bigger and bigger and bigger. So there are now two parameters. The first is the matrix storage engine, templated over type, extents, allocation, and layout. And the second is the operation traits, describing element, storage engine, and arithmetic promotion traits. But why would you want to customize the arithmetic traits? Surely arithmetic is just arithmetic. Let's take a look at multiplication. At worst, to multiply two n-square matrices requires n-cubed multiplications of scalars and n squared minus n additions. That is a lot of work. This means the complexity is O(n) cubed, although there are cache considerations to bear in mind that aren't a part of complexity calculation, but it's a big old job. The ubiquity of matrix multiplication, and there is a lot of it about, really. Matrix multiplication right now. Who's got a phone? Does anybody here have a phone? Yeah. There's matrix multiplication happening right now on your phones whilst I'm giving this talk. So the ubiquity of matrix multiplication has inspired a lot of research into superior algorithms. Does anybody know about Strassen's algorithm? Oh, this is nerd sniping. Great, okay. So that has complexity O(n) to the power 2.807. I have no idea how that figure is calculated. There's something about complexity calculation which I'll leave to the experts. I am just reading a number out here. I recognize this. I don't know how you calculate fractional complexities. I remember when I was at university, I studied, my closing thesis was on fractals because it was 1990 and fractals were cool. And I heard about the Hausdorff metric, which says, what is the dimensionality of this set of points on a plane? And if I said 2, my maths lecturer would just laugh at me. He said, it's not 2. Anyway, so fractional complexity. I do know that there has been a race to minimize this number over the years. If you can do better than 2.807 on a few trillion calculations a day, that's a great thing. As of 2014, that complexity number has reached that. That's the best result. There's been research not just into multiplication, but also Gaussian elimination, matrix inversion, determinant calculation, all for the same reason, because there is so much of it about, leading to all manner of handy algorithms for particular circumstances. So we cannot, therefore, require clients of this class to use a particular algorithm, to use the default naive algorithm. And this gives us our third customization point, the set of algorithms that you want to use for operations on matrices. Now, you may decide on an expression templates implementation of your algorithms, or you may decide that the compilation burden is too great and decide on just something more naive whilst you're prototyping. In fact, we have a context for implementation of matrix multiplication, which filled me with glee. So your custom operation traits may only specialize one particular aspect. So we have to provide a set of defaults. Here we've imported the addition element promotion and storage promotion traits and supplied our own addition algorithm traits. So to summarize your customization options, you declare a basic matrix. You choose a matrix storage engine. You choose an element type, an extent, using a single row or column for a vector, or dynamic extents for runtime decision making. You can choose an allocator if you want the objects to have dynamic storage duration. And you can choose a layout. And then finally, you choose your operation traits. Interestingly, this solves the complex number problem in a roundabout way, because by declaring two matrices of dimension 1 by 1, you can use that machinery to do all of the appropriate promotion. Now, I'm defaulting to row major storage here. The type of C3 will be complex scalar double. I've left a lot out here. I'll pause for any further questions. You are all stunned into silence. Okay, let's crack on. Right, 15 minutes for applications in colour. I might have to race through this. Right, what colour is that? Oh, come on, it's a colour. What colour is that? Red. Good, thank you. Wow, you're terrified of questions, aren't you? It's not red. No, 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 it's purple. No, it's red. What about that one? No. Do you know what? According to PowerPoint, that's orange. I didn't make it up. PowerPoint says that's orange. I don't think so. And it sounds like you don't think so either. The problem we have is one of subjectivity and context, and that's the root of all ambiguity, frankly. The first thing we need to observe is that perception is logarithmic. We've been ram-raided by another talk, by the way. Perception is logarithmic. Differences at low levels are more significant than differences at high levels, and this is fundamental to human behavior, actually. It's evolutionarily advantageous to notice the small things rather than the big things. If you're being tracked by a predator, hearing a footstep in near silence is valuable. If you're being chased by 30 predators, hearing a 31st predator chasing you isn't valuable information. It's little differences. The same is true of sight. If you perceive the amount of light cast by a single bulb, and then suddenly another bulb lights up, the effect is noticeable. It will consume your attention. On the other hand, if you perceive the amount of light cast by 8 bulbs, adding another one isn't going to make much difference to you. And this is about the difference between contrast and brightness. Contrast is more useful than absolute brightness. Mechanical vision is linear. I say linear. It's not really vision. It's photons hitting a CCD. This is a diagram of a CCD chip inside your phones. Vision is about apprehension, understanding, parsing, contextualizing, and that's why it's logarithmic, because that's what is most useful. Machines just count photons using natural numbers. Well, actually, they don't count photons, they take a sample, rather than counting the entire number of photons that are hitting a particular area. The interesting information is at the dark end. Okay? Contrast, not brightness. To improve sampling at that end, we store the square root rather than the value. And this gives us more values at the bottom in exchange for fewer values at the top. It's not actually the square root, I'm overgeneralizing, it's something about, it's somewhere between the power of x, x to the power of somewhere between 1 upon 1.8 and 1 upon 2.2. This number is called the gamma value. You may have heard of gamma. People are nodding. Great. The gamma value. More on this in a moment, but a low gamma that we have at the top samples more evenly across the spectrum than high gamma. Low gamma is good for bright pictures. High gamma is good for darker pictures. And you store the gamma correction out of band in your data so that you can decode it properly. So that's metadata, effectively. What about color, though? Now, there are two kinds of light-sensitive cells in the eyes, rods and cones. Rods apprehend lower intensities, while cones apprehend brighter signals, but they also specialize over particular electromagnetic frequency ranges. There are 3 types of cone, specializing in different ranges. They're labeled S, M, and L for short, medium, and long wavelength. It's very Anglo-centric. As you can see from the picture, the S cones respond to shorter wavelengths, peaking at about 420 nanometers, and there are fewest of them. They make up about 2% of the cones in the human eye. The M cones make up about a third, peaking at 530 nanometers. And the L cones make up the majority. They peak at the longer wavelength of 580 nanometers. You can see that red, green, and blue are the primary colors here. 3 types of cone makes humans trichromats. Although originally we were tetrachromats, 4 types, until genetic mutation got in the way and cut one out. We're left with 3. I've heard it suggested Van Gogh was probably a tetrachromat, and women are more likely to be tetrachromats than men, but they are non-functional tetrachromats. They will have a 4th type, but it's not working. There's been one document example of a functional tetrachromat. She was found in 2016, so it's really rare. But with 3 cones being the general case, we only need a vector of 3 values to represent all of human vision. And what we need is a way of transforming those electromagnetic emissions into perceived color. So what you do is you take a standard human, you put them in a standard environment, and then you measure how they perceive electromagnetic waves via matching the colors of lights. And then you build a function that maps wavelengths to perception, giving 3 values, x, y, z. Then you constrain this function so that all values are positive and luminance ranges from 0 to 100. And this was first attempted in the late 1920s, 90 years ago. These results were combined by the Commission Internationale de l'Éclairage, which in English is the International Commission on Illumination. And they created the CIE RGB color space, from which the CIE XYZ color space was derived. Now, not all values are possible because the ranges overlap. For example, S and L cannot both be 0. So engineering is messy, and engineering is real life. And the vector space defined by this color space contains impossible values. Now, we apprehend brightness separate from color. So let's create a color space to reflect that. So we can normalize the value so that we have 2 values representing color and a 3rd value for relative luminance in form of, brightness. And it's important to emphasize that Y here is the relative luminance, and that's by deliberate choice. I'll go into that in a moment. We have a 2-dimensional color space that we can vary by brightness. And it looks like this. This is the XYY color space. The figures in blue around the edges are the wavelengths. The X and Y vary between 0 and 1, and this diagram displays the maximally saturated bright colors that can be produced by a monitor. The area is called the gamut of human vision. Some interesting properties emerge. All visible chromaticities correspond to non-negative values of X, Y, and Z. Everything you can see is in there. If you choose any 2 points of color on the diagram, then all the colors that lie in a straight line between the 2 points can be formed by mixing these 2 colors. An equal mixture of 2 equally bright colors will not generally lie on the midpoint of that line segment. In more general terms, a distance on that diagram does not correspond to a degree of difference between 2 colors. If you want to go between 2 colors, it's a little bit more complicated. If you choose 3 sources, you'll get a large range of colors, but you won't get the full range of colors visible to humans because that shape is not a triangle. It's kind of triangular, but it's not actually a triangle. I got all of this from Wikipedia. It's absolutely full of stuff, some of which seems to be contradictory. So it takes quite a bit of tricky research. I want to call back to the earlier discussion on how we perceive brightness, because perceptual uniformity is an important property where a small change in a value has the same effect in perceived color, regardless of what the value is. And values in the color space are not very perceptually uniform. This makes it inefficient. So there were 3 further attempts to achieve this uniformity, but they still demonstrate some distortion. Now, in 1996, Microsoft and Hewlett-Packard created the sRGB standard. Who's heard of sRGB? Great, good. It's a standard. The International Electrotechnical Commission, the IEC, formally identified this in 1999. And it's often the default color space for images that contain no color space information. Remember how I was saying that it's stored as metadata? If you just supply somebody with a bitmap of, we don't know, unless we know what the standard is that's being used, we can't really tell what that image is. Now, this color space has 8 integers per color channel, and it's designed for monitors, printers, and the World Wide Web. And as you can imagine, it's the most widely used color space. It defines the chromaticities of red, green, and blue, and the colors where one of the 3 channels is non-zero, and the others are all 0, which are your primary points. They're based on the colors of the phosphors in cathode ray tube TV sets. Who remembers cathode? Is anybody here who never had a cathode ray tube TV set? Oh, you're all quite old. Last time I gave this talk, there were a whole bunch of people who looked at me and said, "What's a cathode ray tube?" But we've had flat screen tellies now for 20 years. It's quite possible. You might wonder if it's still relevant now that the CRT devices are all but extinct. But you can make a tri-stimulus display. That's what they're called when you have a tri-stimulus display that conforms to sRGB. It doesn't have to use phosphors. That's just where the basis is. You can use LEDs of the same color, frankly. In fact, you can use any materials you like as long as the primaries match. So the gamut looks like this. The triangle in the middle is the sRGB gamut, shown within the 1931 gamut. It's all the colors you can see on an sRGB monitor. Each corner of the triangle is a primary defined in XY. You might be thinking to yourself, hang on, what about the colors outside the triangle? I can see those. That's because I'm lying. Those colors are wrong. They're an interpolation, a representation. All you can actually see on a monitor is the things inside. You can't get the full range of human vision inside an sRGB, on an sRGB monitor. It also defines a transfer function. Here's where we're getting to the linear algebra at last. Between the intensity of these primaries and the actual number stored. The function is non-linear, and that word non-linear is really important. The x-axis contains the stored value from 0 to 1. So if you store the value as 8-bit integers, it can be from 0 to 255. On the right-hand y-axis, also ranging from 0 to 1, you have the intensity. So the red plot is the sRGB intensities versus the sRGB numerical values. Nice slope there. Behind that red curve is a dashed black curve showing an exact gamma of 2.2. And as you can see, there is more detail at lower values. The upper half of the intensity spread is represented with only about a third of the stored values. So on the left-hand y-axis, you have the effective local gamma. So the blue plot is the function slope in log-log space, which is the effective gamma at each point. You'll notice that there's a little sort of straight line at the end. And the reason for that is so that we don't end up with it asymptoting off to 0. That would make all the maths very hard. Right. So how do we transfer from RGB back to XYZ and back again? So the first line, so what we have here is a simple linear transformation by the power of matrices, basically. And that's kind of the really important thing with color, is that we get color wrong all the time. When people interpolate color, because it's not linear, they get it wrong. They need to transform into a linear color space, which is what sRGB is, and then perform the interpolation and transform back to where they started. It's quite a problem. It's quite computation expensive as well. For small intensities, you simply need to multiply by 12.92 to do the gamma correction. But for larger intensities, you can see the rather unpleasant activity of taking the 5th power and then the 12th root. That's 3 times per pixel. The 3rd and 4th line are the reverse operations, which go from RGB back to XYZ. It is really computationally expensive. So in summary, brightness perception is logarithmic. XYZ defines absolute perceptual colors. The XYY color space is linear. And linear interpolation is valid only on linear color spaces. sRGB is defined relative to XYY, but the transfer function is not a linear function, and it's really expensive. sRGB is non-linear, which means that linear interpolation is invalid on sRGB. We need to be able to transform between color spaces using matrices. Okay, we're an hour in, so I'll call it a day there. Does anybody have any questions? Thank you very much. There's another version of this talk. If you just search for me and linear algebra, there's a 90-minute version of this talk where I go into a lot more detail about color. There are also, I've given whole talks on color and whole talks on the geometric applications of linear algebra. So do hunt around if you're truly interested.